Hello students, this is Tim Tomalanovich and welcome to Learning Plan 2 lecture notes. We're going to determine how to calculate force systems of concurrent force systems. Determine the resultants of force systems. So there's several of these that we're going to have to learn. Okay. So far you learned what a force is. A force equals mass times acceleration, and that's typically snow loads, wind loads, and most likely weights of materials. And then we also know what a force vector consists of, four characteristics, correct? We have the magnitude, we have the line of action, we have the sense, and we have the point of application. Okay. So those are the four characteristics of the force, because we need to know all those so we can do structural analysis. All right, with that, let's get right into it. Okay, so we are going to determine the resultants of concurrent force system. Okay, what is a concurrent force system? So a concurrent force system is defined as the line of actions intersect at a common point. Okay. So we could have multiple forces acting at a common point in your structure. You know, if you think about bridges, trusses, we have multiple concurrent force systems. So now knowing what a force is, the four characteristics, and how to break it up into force components, the rectangular components, Fx and Fy. Now what we like to do we would rather use one force to determine the design of that connection versus looking at several force connections. And then what this does too is also determines which way is that force pulling. Is it pulling to positive, negative? So, okay. So with that, we're going to do method of components. So looking at this, method of components, the first step is what we do is we need to calculate and algebraically sum the x components for each force, calculate and algebraically sum the y components for each force. All right. So if I look at the figure to the right here, this guy right here. So if you look here, we have a B force vector, an A force vector, and a C force vector. So the first thing I'm going to do is I'm going to break these all into the x and y components. Okay. So here's B, right? This B is the resultant. So we notice it's going to the right and it's pointing up. So my Fy and my Fx better be pointing up and to the right. Here's force vector A. Okay, so actually they kind of overlie on each other. And then force vector C. Okay. The point of common concurrency is at point O. So that's basically what this figure is showing. So if you want, make a little table, Fx, Fy, and now you want to make sure that you're looking at the sense when you sum them up that if I have a negative force, it's being subtracted. Okay. So once I do that, and then what I'm going to do is the sum of Fx forces equals Rx. So that's basically a resultant of the x forces. The sum of the forces in the y direction, that's the resultant of the y's. So that's what I'm going to do next. And then to find the resultant of those, I'm going to take, using the Pythagorean theorem, I'm going to take Rx squared plus Ry squared and take the square root of that, and I'll find the resultant of the resultants, basically. And this will make sense when we do an example. And then once I have, see what happens is we turn this big mess and we turn into this. So we have Ry. This Ry is right there. This Rx is right there. And then once I have my new free body diagram, that's step 4 here, I know my resultant has to be between my y force vector and my x force vector. So here's R. Let's use green. My resultant is the resultant of this equation right there. So looking at this diagram here, if I erase all this, this point of application could be a connection on a wall or something. It is going up and to the right. So this is the magnitude R. This is the magnitude of my force vector is the resulting of that. Now I need to know what is my line of action. Remember, the line of action is the shaft of the arrow. I need to know that angle. Oops, sorry. So theta, if this is a right triangle, opposite over adjacent is tangent. So if I take the inverse tangent of ry over rx, I'll get my theta, which is right there. Oops, let me hit the old erase button here. So here's my theta. Okay, and then I need to indicate sense. So my sense of my resultant is northeast. Northeast, that's up and to the right. Okay, so with that, let's do an example. So I'm doing example problem 2.10 on page 36 of your book. So I'm going to try to sketch it out and talk you through the problem. An anchoring device is subject to 3 forces as shown. Determine analytically the resultant force the anchor must resist. Okay, so step 1, let's draw a diagram. So we have a force going this way, and this is my point of common concurrency. This is my point of application. So that's another thing. The point of common concurrency, where the line of actions intersect, is the point of application, and that works due to principle of transmissibility. So F1 equals 125 pounds. All right. We have a force this way, so there's no angle here, and that is F3, and that equals 100 pounds. And then we have a force. So you notice my sense is acting at point O, and that is F2, and that equals 65 pounds. Now, if I look at my angles, so they give you a slope triangle of 1 to 1 for F2. Okay. And then they give you an angle of 25 degrees for F1 from horizontal. So the first step is they call this a free body diagram. All right, so step 2, we need to break everything into X and Y coordinates. Let's start with F1. Okay, knowing trigonometry, the cosine is adjacent over hypotenuse because F1 is the resultant of that right triangle, and then sine is the opposite. So this is why it's important that you understand trigonometry and how to convert resultant forces into rectangular components, they call. F1x equals negative, because if I look here, here's x, here's y. So the sense of my x force is negative. Negative cosine of 25 degrees times my hypotenuse times 125 pounds equals F the force, F1 force in the y direction. Now that's positive, okay? Because my blue vectors here surround my F1 resultant vector. So that's sine of 25 degrees times 125 pounds. So let's do that quick. So cosine of 25 times 125, I get 113.3. Negative, don't forget your negative, 113.3 pounds. Sine of 25 times 125, that is 52.8 pounds. Okay? All right, so let's do F2. Let's do that in black. F2. F2x. All right, so if I look here, that's my y, and that's my x for F2. We have a slope triangle of 1 to 1, which is a 45-degree angle, or I can figure out the hypotenuse of this, so which is 1 squared plus 1 squared, and that is 1, or 2. 1 squared plus 1 squared is 2, so this is the square root of 2. But I know that's 45 degrees, so however you want to do it. So my F2x is a negative, so the horizontal is 1 over the square root of 2 times 65 pounds, and then F2y equals a negative 1 over the square root of 2, right? This is my horizontal side. This is my vertical side of my slope triangle times 65 pounds. Or if I take 1 divided by the square root of 2, 1 divided by, let's see here, 2 squared equals 0.707. So if I take the sine of 45, that's 0.707. I get the same thing. 0.707 times 65, that's 45.95, so we're going to say 46.0. 0.0, that's a negative because it's pointing to the left, pounds. And then this was also a negative 46 pounds because it's pointing down, the y. All right, so F3, if I look at F3, the resultant of F3 is already on the horizontal axis here. See it right here? So there is no angled resultant, and there's no y component, so we know it's pointing to the right, so it's positive. So F3x equals a positive 100 pounds, and the F3y equals 0 pounds. Okay, so there we go. So this is critical where you make sure you're looking at your senses, determine if it's positive or negative. Make sure you draw your free body diagram correctly. Okay. Now, step 3, so I'll go to the next page, is I'm going to sum, okay, we'll use blue again, the sum of the forces in the x direction equals Rx, and that equals, so I'll go back and forth here. So we have a negative 113.3, negative 113.3 Okay, F2x is a negative 46. So I'm going to add that, but I'm just subtracting it because of addition rules. Minus 46.0. F2x and F3 is a positive 100. So I'm summing these up. That's what my little sum sign looks like. Plus, I'm sorry, what was it again? 100 pounds. Plus 100 pounds. And that equals, all right, so 113.3 plus 46. So that's a negative 159.3 pounds. So I'm going to subtract 100, and that equals a negative, right? This number is negative 59.3 pounds. That equals the resultant of the x forces. Okay, now we're going to sum the forces in the y direction, which equals the resultant of the y directions. So that equals, so F1y is 52.8 pounds. And then I'm going to add F2y, which is negative 46 pounds. So it's minus 46.0 pounds. And then I have 0, and there's no y force for F3. So that equals, so 52.8 minus 46 is 6.8 pounds. And that's positive, 6.8 pounds. Okay. So step 1, free body diagram. Step 2, convert to x and y. And the basic steps are in the previous slide. Step 3, I sum them up. So I'll make this step 3. Step 4, I'm going to redraw my free body diagram. So if I do that, I'm going to do this. Okay, this is x, and this is positive, and this is y, and this is positive. All right, so my x force is a negative 59.3. So I know my sense is pointing to the left. Okay, and then my y is a positive 6.8. So see that this is an arbitrary point of application. This point of application right there is the same point of application right there. They're the same. I'm just cleaning up my free body diagram. So now knowing that, I know my resultant has to be in between those. And then I need to find my theta x. So I created a right triangle. So now step 5, r equals the square root, because I can create a Pythagorean theorem, rx squared plus the resultant in the y direction squared. And that equals minus 59.3 squared plus 6.8 squared, and I take the square root of that. Okay, so 59.3 squared. So let me clear everything out here. 59.3 squared plus 6.8 squared equals, and then I take the square root of that answer. I get 59.68, so 59.7. 0.7 pounds. So 59.7 pounds. Okay? All right, so you notice when you square a negative number, it turns positive anyway, so you're always adding these up. All right, so now, step 6, we need to find theta x, because we know if we make a right triangle, opposite over adjacent, because this is also 6.8, I take the inverse tangent of ry over rx, and that equals the inverse tangent of, so ry is 6.8 divided by 59.3. So make sure you do that in parentheses first. 6.8 divided by 59.3, and I take the inverse tangent, and it's 6.5 degrees. 6.5 degrees. Equals theta x. Now, remember, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, I do believe. So by doing this step 4, we're creating a free body diagram. Sometimes, I'm sorry, see, that's a negative 59.3, so this is actually a negative 6.5 degrees. That is just basically telling you what quadrant I'm in. Okay? Don't worry about your negatives. Look at your free body diagram. I know it is 6.5 degrees from the x-axis, and it's in quadrant 2 by physically looking at it. So don't let the math confuse you because of the unit circle. Okay? So, and now, step 7, my sense is northwest by looking at it right here. Northwest is my sense. So summing up, basically, if I look at that original connection, I have 59.3, 6.8, and my resultant was 59.7. So this is the pound sign. That's what they use in the book. And then I know 6.5 degrees. So basically what I did is this connection, like a truss connection, you'll be able to see the figure when you're looking at the book. I know I have to resist this connection from moving to the northwest. So let's identify our 4 characteristics of the force. We're going to call this point O right here. Magnitude equals 59.7 pounds. Sense equals northwest. Line of action is 6.5 degrees from, x-axis, and then point of application equals O. So this is of the resultant of my resultant. So we can now use this force to figure out how that connection, all those forces, those 3 forces on there, I'm going to react at that connection and how to design that, which will be later in the course. So hopefully that makes sense. So with that, here is your homework Read pages 21 to 22. This is a review. 21 to 30, 29 to 31, 33 to 39, and do problems 2.9, 2.10, and 2.12 on pages 40 to 41. Now, if you want to need more practice, please let me know. I can give you some more problems from a different textbook to get used to this. So this is the end of this lesson. So thank you so much for your attention. Oops. Come on. Trying to figure out how to get my mouse to work in the right spot here so I can actually turn this thing off. All right. This is being stubborn.